Yeah, hi everybody. So as Natalie said, we'll be rocking out some heavy metals tonight, talking about the origins of the heaviest elements in our universe. So just kind of want to do a little bit of a kind of chemistry review for everybody since we're going to be talking about the periodic table and all the elements a whole lot. So here I have our periodic table, and these show all the different elements that we have. And so every single element on here is comprised of essentially three different things: electrons, which are negatively charged, protons, which are positively charged, and neutrons, which are neutral. They do not have charge. And so the protons and the neutrons, those sit in the nucleus of the atom, and that's a very compact space. And then farther out, the electrons orbit around that nucleus. And so the type of atom that we have depends on how many protons you have. That defines what your element is. So for example, here we have carbon with 6 protons, oxygen with 8 protons, and all of those numbers up there, all the way up to 118. And then you have a different amount of neutrons, that does not change your element. It is actually what we call an isotope of that element. There is no actual, besides the number of neutrons, there is no change really to the properties of that atom for the most part. And so, usually astronomers, when we talk about metals, that's basically anything heavier than helium. Here, while that is still kind of true, I'm going to be talking more about the metals we use in our daily lives. So basically, the heavy metals that I'm going to be talking about are pretty much everything starting from about this line here. So this line of elements, this row of elements here, these are what we call the first peak elements, and we'll get into exactly why it's called that later. We can keep going down the periodic table, down starting in our lutetium, keep going, our lanthanides, all the way up to our actinides, all the way down there. And so these are actually the heaviest naturally made elements. We go all the way up to uranium. Anything that's heavier than that, don't really see occurring in nature naturally. So those have all been lab made as opposed to something out there in space. So I want to talk a little bit about the heavy metals that we actually see in our lives. I want to ground this a little bit before diving into this. So I'm sure probably all of you are familiar. Very common heavy element. Perhaps some of you have some jewelry on you right now. Gold. Probably is the most eye-popping one. We all love our gold. It's also very good for space. There are some spacecraft things. There are some other lesser-known ones that are much more common in everyday use. We have things like iridium. Those are very common for spark plugs in engines. So that's how your car is going to go. Very vital for our motor lives. It's also things like silver. Again, jewelry, very popular for that. Also has a lot of antibacterial properties. There's zirconium. Use that a lot for valves and things like that. So, if you need water or fluid to get somewhere, perhaps has a zirconium valve to it. Don't really see that as much every day, but hey, it's there. Iodine, pretty popular. Iodized table salt, used for a lot of health purposes and cancer treatment as well. We also like to light up the night with some xenon for our neon signs. Maybe if you go to Vegas, probably see a lot of xenon out there. Again, technically not a metal, but at least for astronomers, anything heavier than hydrogen and helium is a metal to us. So I'm counting that one. Then we kind of get a little bit more abstract, perhaps maybe some of you have seen some of these things in your daily lives, but at least a lot of the clocks that we have these days might be based off of cesium atomic clocks. They're very, very precise. And then lastly, another thing that maybe you haven't seen as much, but tends to be in a lot of more advanced technologies, neodymium is a pretty common, very incredibly strong magnet in a lot of things. So these are all examples of heavy metals that we use in our daily lives. And so the question becomes, where in the world did these things start from? Well, first, think about it. These things come from mines. We got to go dig them up somewhere. A lot of heavy metals can come out of Africa, or a decent number of mines around the Americas and all that. But, where do the mines get it? Well, come from planet Earth. You know, so maybe we just keep digging, maybe we'll keep getting some more stuff. But we don't really that hasn't still answered the question of where in the world did the Earth get? Because it's got to come to the Earth before it can be in the Earth. So how in the world do we get something like that? And so a pretty good quote I have here from Carl Sagan is, if you wish to make an apple pie from scratch, you must first invent the universe. So let's go ahead and invent the universe and make our way to those very heavy elements. At the very beginning of things, so the universe basically only had hydrogen and helium. Those are the two lightest elements. There are also very, very trace amounts of lithium, but we're just going to ignore that for now. It was essentially purely just hydrogen and helium. So we start with these building blocks. Hydrogen, a singular proton with a singular electron orbiting it. Helium, generally 2 protons, 2 neutrons, 2 electrons that are orbiting. So we got to build up from here and get all the way to uranium, which is 92. And that thing typically has something like 140 neutrons. So we're a long ways away from our very heavy elements. So we got to figure out how in the world we do that. Well, we can start with beginning how to build up some of the lighter elements. And so our own sun, it's undergoing nuclear fusion right now. And so in its very core, it is smashing together hydrogen protons. And don't care about memorizing exactly what's all going on here. It doesn't super matter, but just understand that the takeaway is that in the very core of our sun, it's smashing together a bunch of protons, and that releases energy. And so actually, that energy takes a very long time as it bounces around, hitting a whole bunch of those atoms, electrons, all that stuff, and eventually makes its way out, and it comes out as the sunlight that we see. And so, in this process of nuclear fusion that we have going on here, we're converting a bunch of our hydrogen into our helium. So this is a great first start. There are also heavier fusion processes. There's what's called the CNO cycle, where you also turn your hydrogen into helium with the help of carbon, nitrogen, and oxygen. That's also typically done in stars heavier than our own, but it's another process that can do that. And this process, you can also repeat it for heavier and heavier elements. And so once the star, in its very core, exhausts its supply of hydrogen, it can begin smashing together helium. And that'll produce things like carbon. And you can kind of keep going down the line with heavier and heavier elements. But there is a stopping point. And that stopping point is iron. Stars cannot fuse anything that is heavier than iron. And so how does anything heavier than iron exist? Well, that's what this talk is all about. So I do just want to briefly touch upon, though, that so essentially stars cannot fuse anything heavier than iron because of this graph here, which shows as a function of how many protons you have in an atom, how much energy is holding it together for a given number of neutrons and protons. And so you'll notice that sitting at that very peak up there is iron, which means it is the most tightly bound. It takes the most energy to rip it apart. And so if you start smashing together hydrogen and making helium, you're releasing energy because it's more tightly bound. And so you can do that all the way up to iron. And if you go beyond that, you need an input of energy in order to do that because it is less bound. And energy can't just poof out of thin air. It has to come from something. So you need iron. So you need an energy to be able to put into that. And so that's why we have nuclear fission, which is the opposite direction, where we break up those atoms. So those are uranium nuclear reactors. It's fission. We're splitting apart those atoms. It's releasing energy because it's going towards iron. And so I want to take a moment. I did throw, this is kind of a lot of review and all that stuff and a little bit of new stuff, hopefully. And I want to ask for what questions do you have before I move on with this? Yeah.
I thought oxygen was the heaviest that a star could, or like it stopped that oxygen that it could create, like stop the fusing.
So the question was,
You said iron.
yeah, so the question was, thought it was oxygen that's the heaviest thing. It is indeed iron, because as I have here, it is the most tightly bound element. And so you can smash together oxygen, and that will still release energy, granted. So you can see oxygen's pretty close to the peak. So it really doesn't release all that much energy, but it still does release some.
Is our sun heavy enough to fuse elements up to iron?
So the question was, is our own sun heavy enough to fuse elements up to iron? Well, so in order to be able to fuse iron, you need to be somewhere around 8 to 10 times the mass of our sun. So our sun is not going to be big enough to be doing this. And so ultimately, this is the reason that leads to stars exploding as what we call core collapse supernova. And so the 8 to 10 solar mass range and above, that's where we get our core collapse supernova, because they're producing iron in their core. Because that steals energy and everything just punches down gravitationally once you start doing that.
So you talked about the energetics of individual nuclei. So what's the distribution like? You know, how many iron atoms, you know, in the local cluster or something like that, or just cosmologically as of now, and versus how many helium atoms? You know, what's
Ooh. So the question was, what is,
and how would you measure that?
yeah, so the question was, what is essentially the ratio like helium to iron? I don't have a number off the top of my head, but generally, so astronomers measure, we call it metallicity, and that's why we call everything heavier than helium metals, because it kind of groups everything together. And usually we essentially measure everything against the sun. And so whenever we see an amount of iron out in the universe somewhere, we always kind of say, what is the ratio of this against the sun? And I think solar metallicity, if I remember correctly, I think is a little bit higher iron than like a lot of things that we see. But essentially you can measure the amount of iron by looking at a spectra of stars. And so it's my maybe we won't go too in detail for this, but if you want to ask about this later, we can do that.
Are we, in terms of percent of mass and iron, are we talking 10% of the universe?
Oh, definitely not
Or
10%. Definitely.
10 to the minus 6.
Yeah, very, very, very small. The typical numbers that I see for abundances of stars is something like for every trillion, so 10 to the 12 hydrogen atoms, I think it's something like 1,000 iron atoms, maybe something like that. It might be 1,000 or 100, somewhere around. So hydrogen by far and away, most of it. Awesome. All right. So we've run into a bit of a problem here. We can't really have stars producing through nuclear fusion these very heavy elements. So because so what are we going to do now? We're kind of stuck with it. Well, we've been considering the positively charged nuclei of atoms and smashing those together. So what if we think about instead our neutrons? And adding neutrons is easy, asterisk, you know, you still need some pretty intense processes going on, but comparatively, it's a whole lot easier. And so that's because your neutron is neutral. When you're trying to smash together two hydrogen atoms, it's a proton and a proton, two like charges, they repel each other. But if you have a neutron, there's no electric force on it. It's completely neutral. So it can, for the most part, sail right through. You just have to figure out how you add those neutrons. And so if you start adding neutrons, you get two outcomes. One, that atom now becomes radioactively unstable. And so it's going to go ahead and decay. And in that case, it's generally going to undergo what we call beta decay. And so beta decay is when the radioactive element is unstable and a neutron in the nucleus transforms into a proton and an electron. The electron gets ejected out. There's some other smattering of subatomic particles that come out, but we'll ignore that for now. And so you've effectively just converted a neutron into a proton. It's kind of like a spy. It just snuck through the potential barrier, the electric force that was repelling the protons out. It allowed the neutron in, it unmasked itself, and you have a proton in the middle of the nucleus. And you just made a heavier element. You've increased the proton number. It is a different element now. Or, if you add that neutron and the atom is stable, congratulations, you made another heavier element. Not a different kind of element, but you've still made a heavier element. And so there are, once again, two regimes that you can talk about this in. Either you add the neutrons very slowly and give the element time for beta decay to happen. And so you'll just it'll sample a neutron perhaps every now and then, takes one, beta decays, takes another neutron, beta decays, and you just slowly build up that way. Or you can just add neutrons rapid fire with a neutron fire hose and just give no time for decays to happen. So you just add so many neutrons that this thing becomes incredibly heavy, very unstable. And so there are two names for these processes. There's the slow neutron capture process, the one at a time, when you have just a very slow trickle of neutrons, S process. Or when you have the fire hose of neutrons, R process, rapid neutron capture process, because there's no time for the atom to beta decay. And so we can look here. I have a map of, with the x-axis here is the number of neutrons of a particular atom or a particular isotope, and then the y-axis here is the number of protons. And so every single cell here is a particular isotope. And so the coloring here talks about what the stability of that atom is. And so you'll notice that there's a black strip that runs across the middle of this. That's what we call the valley of stability, because that's where our atoms are going to be happy forever. And so they will not react. Okay? And as you move away from that valley of stability, they become increasingly more quickly decaying. So those that are kind of right nearby, it takes quite a while before those things decay, versus as you go out to these darker blues, it takes less than a trillionth of a second for that thing to decay. Incredibly fast. So then the other feature that I want to point out here also is that you'll notice there's a one-to-one line that's drawn here. And you'll notice that the valley of stability peels away from that. It takes more and more neutrons as you get heavier and heavier elements for an atom to be stable. So let's zoom in on this graph. And I just want to talk a little bit more about our process and its process. And so given a more concrete example here. So I have elements A, B, D, and E. We're starting off with, we're going to start off with element A, 40 protons, 60 neutrons, and we want to make something that's heavy. And so anything that's in gray here, that's a radioactively unstable element. Anything in white, gonna be stable, so it'll stick around for a long time. So if we want to turn this element into something heavier, we have our two options, S process and R process. So if we undergo S process, like I said, it's just a very slow trigger. So first, we add our neutron, it moves to the right, because it increases in neutrons, so we go from 60 to 61, so we move right here. That is an unstable element, it beta decays, it loses a neutron, so it moves to the left on this graph, but it also gains a proton, so it moves up. So it effectively moves up and to the left. And so we can keep doing this. S process, another time later, we add another neutron, beta decays back, add another neutron, beta decays back. We hit this strip up here where it's a bunch of stable elements, so we can continue on our merry way. We're happy. We've just made, over some long amount of time with the S process, we've made element E, which has 3 more protons and 4 more neutrons. So we successfully made a very heavy element. Other option, R process. We unleash our fire hose of neutrons upon this poor unsuspecting element A. We inundate it with neutrons. Perhaps we've just only added these 4 neutrons, and then our fire hose stops, and it beta decays down to that stable element. So you can get some kind of funkier isotopes with our processes. And again, I want to take a moment to pause here. I've thrown a lot at all of you. What questions do you have?
So on that one-to-one graph, and you're below it with more neutrons. So you described the process where the neutron changes into a proton.
Mm-hmm.
What happens farther down here where you have too many protons?
So if you have
Makes it unstable because you have too many protons.
So there is another process. It's essentially, I believe, the reverse of that. So I believe, if I remember correctly, you can have beta decay positive, beta decay negative, and so essentially what happens is you're still booting out. I think essentially you'll be booting out protons at that point, because I think you're kicking out essentially helium nuclei, if I remember correctly. And so you're ejecting protons as well. So you're not just ejecting a singular electron, or you're not transitioning a single neutron into that.
It was an alpha particle.
Exactly. Yeah, so you're booting out more things and getting back to your valence stability.
So this might just be that every function looks locally quadratic, but I can't help but notice that the curve, the map of atomic stability looks sort of like root, like protons equals root neutrons times some constant. I'm wondering if there's any like physical process that explains why the slope looks particularly like that.
I do think it is something. Sorry, I forgot to repeat the question. So the question was why this kind of looks a little bit quadratic. You are approximately right. I think it is something like essentially root number of neutron, or sorry, what would that be? You essentially need you need an increasing number of neutrons for every proton. So I think you need essentially a neutron square for protons as you keep going. And essentially what's setting that is a lot of the strong and weak nuclear forces. That's very detailed and very technical, which perhaps we'll skip over for now, but I encourage you to look up on Wikipedia or something. Yeah.
When you talk about stable, what do you mean stable? I mean, stable cosmologically, or stable, well, the time it takes all the thorium to kind of cool the Earth down, which is only a couple billion, a billion or 2 years.
Yeah, so what do I mean when I'm talking about stable? Essentially, if you let that nucleus sit there forever, it won't change. So anything that is not black here will change eventually. It is a question of time scale. You can kind of think of some of the red ones as effectively forever, because like some of the really dark red ones, those are, that's about 1 billion years. And so, for all intents and purposes, effectively forever, but the black ones, if you truly just let that sit there forever, that would be stable. It will never change. All right, great question. So let's go forward a little bit, back through, and I want to show a quick video of our process in action. So here we have a video, and there's a lot going on here. And so this is the same graph that I was showing earlier, essentially. We have our number of neutrons along the x-axis, number of protons along the y-axis. The coloration here shows how much of that particular material there is. Red is a whole lot, blue, not a whole lot. And then the other thing that I want to point out is up here along the top. So there's this chart, this graph is showing as a function of what's in the nucleus, so the total number of things, your neutrons plus your protons, how much of it is there. And so I'm going to play the video. And I want you to pay attention. I'm probably going to play it multiple times so you can kind of look at each one. And then the other thing that's up here in the top panel is all of these blue dots. Those are what we see in the sun. So those are these solar abundances. And so I'm going to play this just a couple of times. Sure, you can see this. So we initially add a whole bunch of neutrons, we get heavier, we go all the way up, and we see that we're beta decaying as all of these elements shift up and to the left. And so this is now happening over the course of many years and then tens of thousands of years. And so, because a lot of these things take a long time as they get closer and closer to the values filled. I'm gonna play this one more time. And I particularly want you to notice what's going on up here in the top, where you see the abundances are beginning to match almost exactly that of the sun. And so this is a very, very important feature. And this is what we call the universality of our process. Because whenever you undergo our process, you effectively produce that abundance pattern. We have this series of peaks. Remember that I mentioned the first peak elements? That's these right here, this big peak right here. And then we have our second peak and our third peak over there. And so whenever we look out into the universe and we try to measure what metals that we see in a whole bunch of stars, this pattern appears again and again. And this is set by those strong nuclear forces, the weak nuclear forces that's going on at that subatomic level. It's fundamentally nuclear physics that is setting these abundance patterns. And so it seems our process is everywhere in the universe. And so that's pretty exciting. So it seems that we might have our answer here. Our process seems to be contributing a lot of these extremely heavy elements. All right. So now the question is, well, where can we get enough neutrons to start doing our process? I told you that this is a process that occurs, but where in the world does this happen? You know, neutrons don't just start spewing out of fire hoses anywhere. Well, do we have enough here on Earth, maybe? Not so much. We tend to be pretty light elements here on Earth. You know, we still have our heavy elements that we do cool stuff with, but you know, for the most part, I'm made of carbon. You know, it's just six neutrons, 6 protons in there. Not a whole lot of neutrons. Exoplanets. Maybe there's something funky going on out there in space. You know? Maybe there's some pretty weird planets. I know some of my colleagues that do exoplanets are always discovering some pretty funky things. Maybe. I mean, we have our own planets. They don't seem to be made out of neutrons or anything. Probably not. Stars like the sun? No, it did say that we're smashing together hydrogen atoms in the sun, so you know, maybe there's a bunch of neutrons that's going on around there. Bigger stars than our own sun do undergo S process, but you know, that's not really the fire hose that we're looking for. We're kind of running out of options here. Maybe some supernova, something like that, you know, stars explode in big cosmic fireworks. Get a lot of neutrons out of that. That might be pretty cool. This was actually the dominant theory for quite some time. But it turns out you just don't have enough neutrons with that. All right. It's not looking pretty good. Aliens? I don't know. Maybe they have some advanced technology. They're going around the universe blasting everything to neutrons. I don't know. Turns out, neutron stars. It's in the name. A whole bunch of neutrons. So, neutron stars, hence the name, are effectively an incredibly dense ball of neutrons. They're what's left behind after you have those core collapse supernovae. And so when you get above that 8 or 10 times the mass of the sun, you start fusing iron in your core, and that's a death sentence for the star. As we said, you don't get any energy out when you start to try to fuse that. And instead, what happens once you start making your iron, it starts absorbing energy. And so stars hold themselves up with the energy that's released from fusion. And when the iron robs it, there is nothing holding it up at that point. And so it just collapses. And as you collapse all of this material, it crunches down gravitationally. You actually start smashing electrons into protons, and that kind of is the reverse of beta decay. And you start making a whole bunch of neutrons, and you're left over with a neutron star. Of course, if you go even heavier, then there's a point where you start making black holes as opposed to neutron stars, but we'll ignore that for now. And so these things, like I said, are incredibly dense. They're literally nuclear density. All the atoms in my body, they're like 99.999% empty space. Those electrons orbit pretty far out. But neutrons, you can kind of think of it as one gigantic nucleus. These things tend to be something like 1.5 times the mass of the sun, crunched down into about the size of San Francisco. Incredibly dense. I think generally a good like rule of thumb that I've seen is if you were to take a teaspoon of one of these things, don't recommend doing that because you probably won't survive the journey. But if you were to somehow survive the journey and scoop a little teaspoon out of these things, it'd be somewhere around the equivalent of 100 million elephants. Tiny little teaspoon. Incredibly dense. And so these things, we've seen them exist. We observe them as what we call pulsars or magnetars. And so pulsars are essentially these cosmic lighthouses that have a beam of light along their pole. And as they come into your line of sight, you can see the radiation. And these things spin incredibly quickly, hundreds of times a second. On the faster end of things, all the way down, I think, to like a few seconds around. So it is something that is 1.5 times the mass of the sun, spinning 100 times around every second. Incredible. So also, we can't just have this neutron star sitting there. It's not exactly a neutron fire hose or anything. We need to do something. And so that's where our merger events come in. And so if you have 2 neutron stars, or perhaps a neutron star and a black hole, they're orbiting one another. As they get closer, and we'll talk about in a little minute why they begin to get closer, they get closer and closer and closer. Because they're so dense, their gravity is so strong that the gravity felt on one side, the closer side to its companion, is so much stronger than that on the farther side, over that roughly San Francisco-sized distance, that it begins to shred it apart. And that's what we call tidal disruption. Probably some of you, being Astro fans, may have heard of spaghettification from a black hole. It's exactly that thing, same thing, except a little bit less extreme scale. You're being pulled apart by gravity. So, all right, we have neutron stars being tidally disrupted. They're being shredded apart. How do we go about detecting these things? Well, I want to go try to find some R process out there in the universe. Well, we got a few options here. So, once these things collide, you get a number of things out of them. You get kilonova, which is what I study. And so kilonova are the electromagnetic signals, so that's the light that we get from, as you smash these things together, you undergo our process, you make all of those extremely radioactive elements, all those elements decay, and just like how nuclear reactors work, when you have the decaying elements, it heats up the water, it heats up all that shrapnel from the collision, and it glows. And so we can spot that, potentially. We're looking for it. And these things are very rapidly evolving. Whenever we talk about evolution, we normally talk about, galaxies. Those things evolve on scales of billions of years. So that takes a long time for things to change in a galaxy. Stars, those things take, on the shorter end, 10 million years in order to change anything. That's still a pretty long time scale. Also know we talked about supernova briefly, so the ends of stars, those last for something like months. Kilonova, on the other hand, very fast. Those are only days, if not a week. So they're really just a blip in the night. So we got to be really on our game in order to catch these things in action. And then also, we would expect that these things, because of all that radioactive decay, that these things should be showing signs of our process, which is actually a large excess of infrared radiation. If anybody's curious, can talk about it afterwards, but there's a lot of technical details that go into it. But at least for now, take my word that our process produces a lot of infrared light, the same stuff that like snakes use to see their prey. So we have the kilonova signal, that's pretty good. There are also short gamma ray bursts. And so those are essentially these extraordinarily powerful blasts of light. And so these come from neutron star mergers. And we essentially categorize gamma ray bursts as short or long. And so the short ones in particular come from these neutron star mergers. And these things last a few seconds. But it's basically like turning on a floodlight and then turning it off just a few seconds later. It's pretty easy to spot these things when we have our telescopes. And then the last thing that we have here is gravitational waves. And so gravitational waves are quite exciting because this is new to the field of astronomy. And again, I want to take a minute. This is a lot of information that I've just thrown at all of you. I want to ask what questions you have before I get into gravitational waves.
Okay, so those two white beams are the gamma ray bursts, right?
Yeah, so the two white beams in that picture on the bottom, those are effectively the gamma ray bursts. You know, this is an artist depiction. You know, thankfully, we've never been close enough to a gamma ray burst to observe it in such detail. We would be having not a very good time here on Earth if that was the case. A couple of years ago, there was a gamma ray burst that was still incredibly far away. I don't remember the exact distance or anything, but it's still like hundreds of thousands, like maybe billion. I don't remember the exact distance. It was at least like, I think hundreds of millions of light years, something like that. And when that gamma ray burst hit the Earth, there was a detectable change in the ionization state of Earth's atmosphere. It was so powerful. This was towards the end of 2022. So these things are powerful. Thankfully, we're not that close enough to any of these.
You said that this was based on two of the neutron stars coming together and their gravity impacting each other. Are these two, like, is it normal for stars to be in pairs like this? And if not, like, how do they find the other star to crash into? Ooh,
this is a very good question. So, you know, do stars tend to come in pairs? So, there have been a number of studies that look at do stars tend to have siblings? And actually, our sun is pretty weird that it doesn't really seem to have a sibling. As you get more and more massive stars, you're more and more likely actually for that star to have a companion, some sort of binary sibling. And so
recently we saw the sun, something came by the sun. Looked like that maybe they would somehow merge together.
I think you might be referring to the interstellar object, I think Oumuamua, from a few years ago. I think it sailed pretty cleanly out of the solar system. I don't think there was any collision or anything.
Is that what did you know that was gonna happen? I mean, as a scientist, as an astronomer.
I know people
think it might
Yeah, I think people were very excited about that once we saw that thing coming. That isn't exactly my area of research. But I know there are a number of people here in the department that do that kind of research, and they were very excited about it when it was spotted. I think we'll do one more question then.
What's the difference between a supernova and a kilonova? The cool name.
Yeah. So difference between a supernova and a kilonova. So supernova are essentially so it is essentially the terminal event of a star. And so there are a few different kinds of supernova, but the main one we've been talking about is that core collapse supernova, where those really massive stars, they start attempting to fuse iron, but as we learned, that is a no-go. And so they essentially implode on itself, it collapses gravitationally, and all that matter that's on the outside, as it falls inwards, slams into the surface of a newly formed neutron star, and bounces off and goes flying into space. There are, of course, some more details other than that, but that's kind of the general picture. And then kilonova, so those are, there's still kind of, still kind of a cataclysmic explosion kind of thing. You still have the crashing of neutron stars together. But the kilonova purely comes from, all of its light come from the radioactive decay of all of those elements that I've been talking about.
So a kilonova is not a supernova, it's not the end of the star's life.
No.
It's like two neutrons.
Yeah, two neutron stars come together. All right. All great questions. So, talk a little bit about gravitational waves for a moment. And you'll see why in just a minute. So these gravitational waves, I mentioned, is kind of a new window into astronomy. These are quite literally ripples in the very fabric of space-time itself. And so these things are caused by whenever masses accelerate. So technically right now, as I wave my arm, I'm producing gravitational waves. We're not going to detect them anytime soon because this is incredibly weak. I don't think I'm that chubby or anything, but I'm not making gravitational waves. And so the stronger the gravity of something, the stronger its gravitational waves are going to be as it accelerates all over the place. And so once we get to our black holes and neutron stars, their gravity is pretty intense. And so you can produce a lot of gravitational waves out of that. And so once you have your two neutron stars, after they've been born together, they go supernova, have two neutron stars left, they begin to go around each other. They emit these gravitational waves, and that's an energy. They're emitting waves, and so they get closer and closer and closer and closer until they smash together, give us our wonderful. And so gravitational waves were actually predicted by Einstein in 1916, and it took 99 years before we were actually able to directly observe them with the LIGO collaboration. So I have a picture of it here in the top left there. That's one of the instruments that they have. It's at Hanford in the United States. And so that thing, each of those little kind of sticks that's coming out of it, those are 4-kilometer long arms. And I'll tell you a little bit more about what's going on inside those arms in just a moment. But essentially what this thing is measuring is the change in distance, which we call the strain. Because as a gravitational wave travels through, you can see this GIF that I have up here in the top right. It stretches and compresses space as a gravitational wave goes through. So in this picture here, the gravitational wave is going through the board. And so at one instant, it compresses along, say, this direction and stretches in this direction. And then a little bit later, stretches in this direction, compresses in up. And so these are incredibly small changes. I cannot emphasize that enough. Over the course of those 4-kilometer long arms, LIGO is able to measure a change of a fraction of the size of a single proton in distance. Incredible. And so to kind of give you like a little bit more perspective on that, because I don't expect all of you to know exactly how big a proton is, in your everyday lives. If you were to consider the distance from the Earth to the sun, that change, so if LIGO were to be that entire distance, it is the same as measuring the change in a nanometer of its distance, of the Earth's distance from the sun. A billionth of a meter, a billionth of about this, over the entire distance from here to the sun. Mind-boggling to me. So I also want to just quickly show a pretty cool video about how this thing works. So this is what's going on inside these arms. So you have here a laser. I'm going to probably pause this quite a bit. So there's a laser that's emitted. It hits a beam splitter right here. So the laser gets sent into 2 halves down each arm. They travel all the way down those 4-kilometer arms, smack into a mirror, and bounce back, and then recombine and hit a detector over here. And so, if we look a little bit more closely at what's going on, so the beam splits, the laser goes along, hits the mirror, bounces back, and recombines. So you'll notice right here, so light is a wave. And so it's going through the universe as a wave. There are peaks and troughs, just like there are ripples in a pond. And so because light is a wave, if you have two photons that are precisely the same, and you offset them by just enough, such that the peak of one wave is perfectly in the trough of the other, they cancel out. And so LIGO is perfectly set up such that as the laser goes along the arms and bounces back, it will perfectly cancel out when the beams recombine. And so that's what you see here. There is no laser. And that's because the distance of those arms is very precisely tuned. And so, if we introduce a change in distance, they no longer perfectly cancel out, and you get a little laser signal. And so you can measure those incredibly small changes in distance of this. An incredible feat of engineering. I cannot fan out over this thing enough. All right. So I've been talking a whole lot about, wow, this is some cool theoretical stuff. Kilonova, our process, wow, fantastic, smashing neutron stars. Some of you might be like, yeah. Have we ever actually seen this? You know, you keep talking, but you know, where's the evidence? Where's the proof of this stuff? Well, perhaps some of you are some astro people and may know the notorious night of August 17th, 2017. We have our gravitational wave signal. And hopefully, I think I've set this up correctly, that it should currently play. So along the x-axis here of each of these plots, that's time. And then essentially the color here is the intensity of a signal, and the y-axis here is the frequency of that signal. And the frequency of the gravitational waves just so happens to be in the human auditory range. And so with these three detectors, so I only showed you a picture of the top one up there, we can actually listen to the universe. And so hopefully I've set this up correctly. Starts out really low. You can't really hear a whole lot. It's a very weak signal. I'm going to shut up now, so once it starts, you should be able to hear it. It's a little bit of a fine signal, but that little, that's the merger event. The two neutron stars just collided with each other. So this was a fantastic signal to get. This was wake you up in your sleep kind of a signal. And so not only did we have the gravitational waves, but also about 2 seconds after that, we spotted a short gamma ray burst, which comes from our neutron star mergers. And also, it's another very interesting scientific thing about that slight time delay, but we'll potentially talk about it later. So that's a pretty good sign. We have a gravitational wave event. We have a short gamma ray burst. Here's a plot. It's a little bit confusing, but just notice that. So that blue blob is where the gamma rays were coming from, where the uncertainty region was. And that kind of green, like pea-like thing, that's where LIGO was saying that the gravitational wave signal was coming from. And you'll notice they overlap. They're probably coming from the same thing. That's pretty exciting. They're coming from the same place. We have two different signals. And what's a little bit unfortunate is this happened during the daytime. And so it was 11 agonizing hours later before we could point our telescopes towards this thing. But when we did, and when I say we, not me, but actually one of the research faculty right here in the department, Ryan Chornock, saw a little blip that wasn't there before, right next to that galaxy. Incredibly close by. I know that this number is probably meaningless, but most things that we talk about are probably billion, hundreds of millions of light years away. This thing is a lot closer. This thing is probably only closer to like, I think that's something like 100-ish million light years. Most of these events happen at billions of light years away. So this is incredibly close. And so, astronomers across the globe pointed our telescopes at this object, collecting data across all these wavelengths, as much as we could possibly get. Because this event, I've heard some general statistics that the combination of this event being so bright, so nearby, something like it would only happen 1 every 10,000 years. So pretty lucky that this happened. And also, a little caveat, we almost actually didn't detect this because the LIGO collaboration, so there were some technical difficulties going on with, so one of the components is Virgo. There were some technical difficulties going on, and so it was down for a while. And they actually extended how long they were going to observe by a month. And this happened in that month. So pretty lucky that there were some technical difficulties, I guess. Not good for technical difficulties, but pretty good thing for that to happen. So we collected so much data on this thing. You can see, so on this graph over here, this is data going from the extremely high energy X-rays over here on the right, all the way down to radio. So like kind of the same thing that, you know, your car picks up from music. And this little kind of tilde thing, that's our kilonova. And you'll notice it vanishes pretty quickly over the course of about 2 weeks. Granted, there's a pretty sizable time gap in between that and the next observation. Unfortunately, it did go behind the sun shortly after that, so not great timing, but hey, we'll take what we can get. And then we have some more detailed data over here, where we have the bluer colors are kind of the bluer light, and that is decaying really quickly. That's gone after just a few days. And as we get to redder and redder wavelengths, as we go closer and closer to the infrared, it's lasting longer and longer. And you'll notice that's our R process signature. So we just watched with our very own eyes, hundreds of astronomers across the globe. We just watched the signatures of our process. We just watched the birth of a whole bunch of those heavy elements. Pretty phenomenal. And we watched it not only with light, but also in gravitational waves. There's a whole lot of technology that went into all of these discoveries, and it just blows me away every single time. We've witnessed the production of the heaviest elements in the universe. We know where these things come from. Our process from the collisions of these incredibly dense neutron stars and possibly black holes too. I'm going to put up some wrap-ups and future questions things, but if there's anything that I want you all to take away from this presentation, it's that if any of you have, some jewelry or you took a car here, you were able to do that because some billions of years ago, before the Earth formed, probably a neutron star merger event that happened that produced that iridium in your car's spark plug, that produced the gold that you wear around your rings. So that gold, that iridium, all that stuff took a long journey to get here under some pretty extreme conditions. So I'll leave this up. Thank you so much for your attention, and I'm happy to take any questions.